Problem 2. Imagine a copper wire 10 kilometers long that needs to supply a city with 10 megawatts of power, say from a waterfall. If the city ran on DC power with voltages of 100 volts, how much current would run through that wire if you were willing to lose 1% of your power as heat in the wire? How thick would such a wire have to be? Resistivity of copper is 1.7 times 10 to the negative 8 ohm meters. Okay, so the way we're going to look at this is as a pretty simplified circuit, where we have something supplying some power through some line, where this line itself is going to have some resistance. It's eventually going to reach the city, which is also going to act as its own resistor. And then it'll complete the circuit. So we'll call the line resistance R line, while we call the city resistance R city. Cool. So we know that across the city, the power supplied to it, we're told, has to be 10 megawatts. 10 megawatts, which could also be written as 10 times 10 to the 6 watts. We also know that we want the city to run on DC power with voltages of 100 volts. So we know P city is equal to 100 volts. And the first thing we want to find is how much current would run through that wire. So for this, we're going to use the equation P is equal to IV, where this is just power is equal to the current times the voltage. We're going to solve for current, I, by dividing by the voltage V to get current is equal to the power divided by the voltage. So we're going to plug in that 10 times 10 to the 6 watts, divide by 100 volts, and that'll leave us 10 to the 5. That is the answer to the first part of the problem. Okay, so for the second part, if you were willing to lose 1% of your power as heat in the wire, how thick would such a wire have to be? Okay, so for this, what we're going to do is we are going to use the two equations. Specifically, the equation for resistance R is equal to rho L over A. And we're going to use this in conjunction with the power equation. P is equal to IV, and specifically the equation for voltage lost over a resistor, P is equal to IR. So starting off with the first equation, R is equal to rho L over A. R, of course, is just our resistance, while rho is the resistivity, which we are told, actually, that the resistivity of copper is 1.7 times 10 to the negative 8 ohm meters. Perfect. L, of course, is just the length of the wire, and A is the cross-sectional area. So if we were going to look at our wire, look, something sort of like this. It has some length L, which we are told is 10 kilometers. It has this innate resistivity rho, and the cross-sectional area is just if we took the area of the circle that made up the cylinder that is our wire. So remember, what we're looking for is how thick the wire should be. And of course, the thickness of the wire is contained in that cross-sectional area A. So ultimately, that's what we're going to be looking for. Which means that we're actually going to have to find the resistance of this line, which we can do by using the power equation, P is equal to IV, in conjunction with the voltage equation, V is equal to IR. So what we're going to do is we're actually going to plug in V is equal to IR into P is equal to IV to get P is equal to I squared R. Just another power equation. So once we have this, we can use the current we found in the first part, 10 to the 5 amps, and the power, knowing that we only dissipate 1% of the original power, and we can use that to find the resistance. Right? So I'm actually going to move this down here. So if we have P is equal to I squared R, we divide both sides by I squared to get ourselves R is equal to P over I squared. Plugging in P, we have 10 times 10 to the 6 watts. But remember, we're only going to dissipate 1% of this. So we're also going to multiply it by the fraction 0.01 to get that fraction, and divide by the current we found, because the current that's going through the city has to be the same current that's going through the rest of the wire, because there's nowhere for it to branch off. And so I, 10 to the 5 amps, and that's squared because it's P over I squared. And this gets us a value for resistance of 10 to the negative 5 ohms. Okay, so with that, we now have a resistance. We already have rho and L, which means we can now go ahead and solve for A. So we're going to take the equation R equal to rho L over A. We're going to multiply A to the other side, divide by R, so that we end up with an equation for which we can solve A. And we get the area is equal to rho L over R. So here we could just plug everything in. 1.7 times 10 to the negative 8 ohm meters times L, 10 kilometers, which we're going to plug in that 10 to the 3 to put it into meters, and divide by the 10 to the negative 5 ohms that we just calculated. In doing this, we should find that the area comes out to be 17 meters squared, which is close to a final answer, right? We want to find out how thick this wire is, which means we want to know what the diameter of this wire is. So that would mean the area of a circle, of course, is just pi r squared. So we want to solve for r. So that's just going to be r equal to the square root a over pi to the square root of 17 meters squared over pi. And we find that the radius comes out to be about 2.3 meters, which means the diameter, which is of course just twice the radius, comes out to be 4.6 meters. And that is how thick our wire has to be, which is really big, actually. And you might notice that you don't see wires like this hanging around the city all over the place. It's actually why voltage is transformed to make high V's and low currents instead of really high currents, such as 10 to the 5 amps. Okay, so that's problem 2.